Alright, this is an introduction for the Atwood Machine lab. It's pretty straightforward. What you're going to do is you're going to click on this link and it's going to set up an Atwood machine. And what I want you to do is I want you to just go ahead and pop open the simulation. You're going to click on the begin button, and we want to run this thing with the default settings. We're going to have 100 grams on one side and 105 on the other, and we are on Earth. So here we have a virtual motion sensor, and all we're going to do is we're going to observe this mass as it moves in the upwards direction. Here we have the position versus time graph. It is parabolic, as you would expect, because, well, it is accelerating. Right down here we have the velocity versus time graph, and what you can kind of do is you can kind of use some values on this to say, hey, I know what the change in velocity was. I know what the change in time was on that guy, and I can record these guys. And that's exactly what I have you do. So I have you go ahead and sketch them, record the change in velocity and the change in time. And something that you should always remember is we know the most basic definition of acceleration is the change in velocity over the change in time. So we're going to say acceleration is the change in velocity over the change in time. Show me one sample calculation so that you know what is going on right here in this little space, and please do include units in that space. Then what I'm going to have you do is I'm just going to have you mess around with the masses. So I'm going to have you repeat this with 125 and 100, 150 and 100, and 200 and 100. As you would probably expect, the acceleration should go up as you increase the mass on the heavier side. With regards to this column right here, the theoretical acceleration and the percent error column, I'm going to have you fill that out in just a little bit, so don't worry about them for right now, but yes, you will come back and fill them out later. Then I'm going to have you do a similar experiment, but I'm going to have you keep a constant mass difference. I want you to make a prediction. Will the acceleration remain constant as you add mass equally to each side? Explain why or why not. And again, I don't care if your prediction is right or wrong. In fact, there's a really good chance that your prediction is not going to be right. I think we learn things when that happens. So you're going to repeat the experiment, recording delta V, delta T, and measuring the acceleration. Again, don't worry about these two columns. You're going to fill them out in just a little bit. Was your prediction right? Why or why not? And what explains this? Then I'm going to have you come over to this part of the lab, and this is when we're going to come out with the theoretical acceleration. And what I'm going to have you do is I'm going to have you draw Newton's the free body for each of these two masses. Keep in mind that this guy was moving down and this guy was moving in that direction. And all I'm going to have you do is draw the free body and write Newton's second law for this one, write Newton's second law for that one, and then come up with an expression for the acceleration in terms of just mass 1, mass 2, and gravity. Yes, I know that you've done this in the lecture problems, but it builds character. It's good for you. Then what I'm going to have you do is I'm going to have you fill out the calculated acceleration in the table, and then you're going to come down here and calculate what your percent error is. Again, if your percent error is rather large, then something bad happened, and you better be looking at your algebra up here, or you better be talking to me on Zoom or via email.